All right, so I'm just going to jump right into starting our brief calculus class. This is kind of my third try at doing this video. I wasn't really happy with what I said the first two times. Not sure I'm going to say anything better this time, but I tried to fill it up with some theory on my lecture and it was kind of clunky. So maybe I will try to record a calculus kind of theory, what calculus is video, or find one on YouTube and post it on my website to keep that kind of free of my lecture here. There's a little bit of algebra we need to remember and in our class. And as we need to remember algebra, I'm just going to introduce it. And the first bit of algebra involves evaluating functions that are given, shown as graphs. And I'm not sure my picture shows up well enough here, so let me try to emphasize the points that I have marked on this graph and how they're marked. The point -2, 0 is marked on this graph with a solid circle. The point 1, -3 is marked on this graph with an open circle. The point 1, 2 is marked on this graph with a closed circle. The point 5, 2 is marked on this graph with an open circle. The point 5, 10 is marked on this graph with a closed circle. And the point 6, 0 is marked on this graph with an open circle. So there's 6 points marked on this graph, some of them marked with open circles, some of them marked with closed circles. What I'm going to need to do is answer function questions with regards to this graph. So this graph is considered the graph of f of x, and I'm supposed to answer some questions. When I'm given function notation, a number inside of parentheses generally represents an x, and it definitely represents an x in this case. This question right here, to find f of -2, this is asking me to find the y value of any point that has x equal to -2. So in this little blurb here, the -2 represents an x, and without saying it, but it's implied, as I'm going to find the y of any point on the graph that has an x of -2, and that's that point -2, 0. -2, 0 is the point that has an x equal to -2. Its y is equal to 0. The answer to what f of -2 is just 0. When I move on to answer what f of 1 is, f of 1 is the y coordinate of any point on the graph that has a an x equal to 1. Well, there's 2 points that are marked with x equal to 1. The point 1, 2 that's marked with a closed circle, and the point 1, -3 that's marked with an open circle. Points with open circles aren't considered part of the graph. They're just kind of the edge of a graph. Here, it's the left edge of the bottom part of this graph right here. And this point 1, -3, because it's marked with an open circle, it's not considered a point on the graph. The only point on the graph of the function that has an x coordinate of 1 is the point 1, 2. And the answer to what f of 1 is going to be 2. If you wrote 2 comma -3, it's not quite right because the point 1, -3, it's not considered a point on the graph. It's marked because maybe it's important. It's definitely the edge of this bottom part of the graph, but it's not considered a point on the graph. Points marked with closed circles are part of the function. Points marked with open circles aren't part of the function, but they might be important as we do computations. The next part, to find f of 5, again, there's 2 points marked with an x coordinate of 5, the point 5, 10, and the point 5, 2. The point 5, 10 is considered a point on the function because it's marked with a closed circle. The point 5, 2 marked with an open circle is not considered a part of the function. So the answer to this third function question is going to be 10. Lastly, to do f of 6, if I had 6 marked on the x-axis, you'd see that the graph only has one point. There's no other points that have an x coordinate of 6. So the only point, there's only one point that has an x coordinate of 6. Its y is 0, but this point is marked with an open circle, so it's not considered a point on the function. When there isn't a point with the x coordinate that's in the parentheses marked with a closed circle, then there isn't a y value. For this, I can say, what is f of 6? Well, it's undefined. I don't know what it is. And sometimes instead of saying undefined, I say does not exist with DNE. That's common notation in our class. These would both be good ways to express what f of 6 is, because there's no point on the graph that has an x coordinate of 6. That's just algebra, but that algebra is going to be important. It's going to kind of link us to calculus. And the big link between calculus and algebra is something called the concept of a limit. And that's what this whole section is going to be on. We're going to learn what a limit is and how to find limits, and maybe I'll say something profound on how it connects algebra to calculus. Anyways, a limit of a function is a y value. So limits are y values. So anytime I'm asking you to find a limit for a function, I'm finding a y value. Just like in the first 4 problems, when I asked you to find f of some function, I'm finding a y value. That's super common. When we're asked to find values with functions, whether they're f of somethings or limits of functions, we're usually looking for y's. The limit of a function is a y value that a function gets closer to as x approaches some given number that I'm going to make up for you. I'm going to tell you, find the limit as x gets closer to this number. We'll start off with the number 4. So the limit describes how a function behaves near a point instead of at that point. This, for me, is beautiful because I already know what a limit is. If you don't know what a limit is, this is probably just garbage. But after we do the lecture, if you need to review, you can go back and read this with some base knowledge, and then it'll probably make a little more sense what I have written here. So let's start by just start learning the concept of a limit by looking at this function x squared minus 16 over x minus 4. And specifically, I'm going to try to find the limit of this function. I'm going to find the limit of the function x squared minus 16 over x minus 4 as x approaches some number. So as x approaches, and the sum number is going to be 4. 4 is a special number because it's not in the domain of this function. So we're going to look at this function. First of all, I want us to notice that this function is undefined at f of 4. So I'm just trying to set some stuff up to make the lecture flow a little bit better. I'm not sure how well it's going to flow, but I'm trying to set up some knowledge that we need to have to understand the concept of limit. So if I plug 4 in for each of these x's, in the numerator I get 4 squared minus 16, changing that x to 4. In the denominator I get 4 minus 4. The numerator becomes 16 minus 16, which is 0. The denominator is 4 minus 4, which is 0. And we all know, some of us know, that 0 divided by 0 is undefined. So when you plug 4 in, you get undefined. The function x squared minus 16 over x minus 4 is not defined when x equal to 4. In an algebra class, we might say 4 is not in the domain of the function. But I can still talk about the y value that the function gets closer to as x gets to 4, because the limit it describes how a function behaves near a point instead of at a point. At the point x equal to 4, the function behaves that it's undefined. But near x equal to 4, maybe it has a behavior that's better than undefined. And this is what the limit is. The limit is the behavior of a function as we get really close to some value instead of at that value. At the value of 4, the function is undefined. Near 4, maybe it's not undefined. So let me read through this. The limit of the function as x approaches 4 is the y value as x gets infinitesimally close to 4. The limit again describes how a function behaves near a point instead of at a point. Again, this is maybe a little too much theory, but it's kind of necessary. I sketched a graph of x squared minus 16, and I'm going to use this graph to help you understand visually what the limit is as x gets closer to 4. You'll notice that this graph has a hole at x equal to 4 as opposed to an asymptote. Sometimes when we graph fractions, numbers that aren't in the domain produce asymptotes on the graph, vertical asymptotes. Sometimes they produce holes. This graph gets a hole at x equal to 4, in this case at the point 4,8, specifically because if I wanted to graph this function, I can graph a simplified version of this function and they'll graph essentially the same. The function that I wrote, x squared minus 16 over x minus 4, if I factor the numerator, I would be able to cancel the fraction and get x plus 4. So my graph, the graph of x squared minus 16 over x minus 4 is virtually identical to the graph of y equals x plus 4, f of x equals x plus 4. In fact, the graph of y equals x plus 4 would be this graph without the hole. The only difference between this function and this function is in this function I can plug 4 in. When I plug 4 in, I get 8. And this function, when I plug 4 in, I get undefined. Other than the point that's not in the domain of this function, these functions are equal to each other for every other value of x. And that's why the graph comes out to be a line. So let's go more into our limit computations. And this is kind of right now just theory and not really the algebra. I could probably just do the algebra without explaining the theory and it'd be a lot easier probably, but I feel obliged to explain some theory. So again, I'm trying to find out how this function behaves as x gets infinitesimally close to 4. I'm trying to find the y value for the function as x gets closer and closer to 4, but not at x equal to 4. This function at x equal to 4 is undefined. But at really close values to 4, maybe those values are approaching some number, and if they are, that's what the limit is. These three questions are asking the same thing, and this is the new notation for this first chapter. So find the y value of the function as find the y value of the function as x. Find the y value that the function approaches, maybe comma, as x gets closer to 4. And this is a symbolic way to answer that question. This says, this limit notation with the little x with an arrow approaching 4, this asks me to find the y value as x gets closer to 4 of that function. And I called this function f of x, so these are interchangeable. I could use f of x or x squared minus 16. So all three of these are asking me to find a y value when x gets closer to 4. The y value when x equals to 4 is undefined, but the y value as x gets closer to 4 may not be undefined, and that's what I want to show you graphically, how I can explain what the limit is. It's not rocket science. So I made up a few pages of algebra to help us. So my goal is to figure out what happens to the y value as x gets closer and closer and closer to 4. So how am I going to figure out what happens to the y's as x gets closer and closer to 4? Well, I'm going to start plugging in numbers close to 4 and then progressively closer to 4 and see if I can predict what's happening to the y's. So I randomly picked a number that's kind of close to 4. 3 is kind of close to 4. It's close to 4, but it's less than 4. I plugged 3 into the function and got 3 squared minus 16, which is 3 squared minus 16 is 9 minus 16 in the numerator. And I plugged 3 for x in the denominator and got 3 minus 4. That gave me negative 7 over negative 1, which is 7. So the x value of 3 gives a y value of 7. I want to find out as x gets closer to 4, do the y's start to get closer to some number? And in order to do this, I need to start at a value of x and then progressively get numbers that are closer to 4 and see if the y's start to approach some number. So the first thing I did is I plugged in 3 and got 7. 3 is not particularly close to 4. I mean, it's an integer away, but it's not particularly close for limit purposes. We need to be infinitesimally close. So I took another number, 3.5, and plugged it into the function. So when I plugged 3 into the function, I got 7 for x. When I plugged 3.5 into the function, I used my calculator and got 7.5 for x. So I picked a value closer to 4 than 3, and my y got bigger. My goal is to say, if I pick a value that's infinitesimally close to 4, what's the y get? Is the y going to get close to some number? And it's not even rocket science to figure out what that number is. It's kind of staring at me already. So let me go and do another example. The next thing I decided to do, so first I picked a number 3, which was close to 4, but not particularly close to 4, and got 7 for y. Then I picked the number 3.5 and got 7.5 for y. That's close to 4. I'm trying to find the limit when x is equal to 4, so I'm trying to pick values that are progressively closer to 4. The next number I picked was 3.9. When I plugged in 3.9, I got 7.9. And so this is my x value, this is my y value. My limit, the limit as x approaches 4 of this function, x squared minus 16 over x minus 4, is the y value that the y's get closer to as x's get closer to 4. Graphically, you could see that this, when I plugged in 3.9 for y, I got a point that's almost bang on that open hole. That open hole is actually what the limit's going to be. The y value of that open hole is going to be the limit. Let me show you one more. So I started off, I plugged 3 in and got 7. I plugged 3.5 in and got 7.5. I plugged 3.9 in and got 7.9. On this one, I go to the function, I plugged 3.99 in, and I get 7.99. So when I plug x values in that are less than 4 but progressively getting closer to 4, what happens to the y's? Well, the y's are less than 7 but getting progressively closer to 8, should I say? The y's are less than 8 but getting progressively closer to 8. To me, looking at this pattern, I can maybe predict that the limit as x approaches 4 is going to be 8, because I think the more values I plug in the x column that are progressively closer to 4, if I plugged in like 3.999 and then 3.9999, the y's I think are going to continue this pattern and get closer and closer to 8. That's my conjecture. So let me formalize that on this next sheet. So on this next sheet, I wrote some calculus down. So now I can make a conclusion about the y values that my points are approaching as the x values get closer to 4, but I only picked x values that were smaller than 4. I picked 3, 3.5, 3.9, 3.99, all values that are smaller than 4. So each one of these statements are true and equivalent statements. As the x values that are smaller than 4 get closer to 4, the y values get closer to 8, because I went from 3 to 7, 3.5 to 7.5, 3.9 to 7.9. So as the x values were all smaller than 4, the y values were all smaller than but got closer to 8. So this is verbally what I did. This is without having any idea of writing calculus. This is the way to use the limit symbols. So I introduced the limit symbol on the previous screen, and I snuck a little exponent here, or a little negative sign, on top of the 4. If somebody that understands math would understand that these mean the same thing. As I plug values into the function that are less than 4 but closer and closer to 4, the y values get closer to 8. This guy right here, when I'm only plugging numbers smaller than 4 into the limit, this is called a one-sided limit, because I'm only plugging numbers on one side of 4, on the smaller side of 4. And specifically, because on a number line, the numbers that I were plugging in were to the left of 4, I might call this a left-hand limit. So I might say the left-hand limit of the function x squared minus 16 over x minus 4 as x approaches 4 is 8. So this is what I just did now. I went through the graphical process of finding a left-hand limit. A left-hand limit is a process of finding a y value that the function gets closer to, starting with values that are smaller than the given value of x. I started with numbers that are smaller than 4. Next thing I'm going to do is find a right-hand limit. And a right-hand limit is just the opposite. So I'm going to repeat the process, but I'm going to start with values of x that are larger than 4 and then get progressively closer to 4. This process is called find the right-hand limit. So now I'm just going to repeat the process. I'm going to try to find the limit as x approaches to 4 by starting with numbers bigger than 4, plugging them into the function and seeing if I can see a pattern. So first I plugged 5 into the function. Again, the function is x squared minus 16 over x minus 4. I did all these pluggings on my calculator, but I could have done them all by hand. To plug 5 into the function, I can go 5 squared minus 16 over 5 minus 4, which is 25 minus 16 over 1, which is 9 over 1, which is 9. So when I plugged 5 in, which is a number that's bigger than 4 but not particularly close to 4, I got 9. And you can see graphically that point that I just found is a bit north of the point 48. I repeated the process. First I plugged 5 in and got 9. And then I picked a number that was bigger than 4 but a little bit closer to 4 than 5. I picked 4.5. And when I plugged 4.5 in, I got 8.5. The first point I found was like the point 49, which wasn't particularly close to the point 48, but kind of close. The next point that I find, 4.5, 8.5, is even closer. If I repeat the process and plug in 4.1, when I plugged in 5, I got 9. When I plugged 4.5 in, I got 8.5. When I plugged 4.1 in on my calculator, I got 8.1. And I could have probably already predict what the right-hand limit is as I start to take values that are progressively closer to 4 but bigger than 4. The y's are going to approach some number, and that number is what the right-hand limit is. You know, graphically, already between the point 48, 8 is going to be the limit, and the point that I have graphed, you can almost not tell the difference between the graphs. And then the last point I plug in before I actually call the limit is 4.1. So I started at 5 and got 9. I plugged in 4.5 and got 8.5. I plugged in 4.1 and got 8.1. And on this screen, I plugged in 4.01 and got 8.01. It seems to me that this right-hand limit, plugging numbers in that are bigger than 4 but not equal to 4, they're approaching the same value. In fact, graphically, the first set of functions that I graphed, the points started beneath this and got closer to that 0.48, and then these points start above the 0.48 and get closer to 8. So I think this right-hand limit is also 8, and that's going to be the case here. So now I can make a conclusion about the y values that my points are approaching as the x values are getting closer to 4 but remain larger than 4. So each one of these statements are going to mean the same thing to somebody that reads mathematics or reads calculus. So as the values of x that are larger than 4 get closer to 4, the y values get closer to 8. And that's what both of these symbols mean. When I use the limit notation tells me what y value asks me to find what y value the function gets closer to as x gets closer to some value. When I put a little plus sign with the limit, that means the numbers that I'm testing are numbers bigger here, in this case bigger than 4. When I put the minus, the numbers I was plugging into the function had to be less than 4. This is also another one-sided limit because I was only plugging in numbers that were bigger than 4. And because the numbers were bigger than 4 as opposed to less than 4, it's specifically called a right-hand limit as opposed to a left-hand limit. In the first example that I did, I plugged in numbers less than 4, and I got this. I got the limit as x approaches 4 from the left side, or by plugging in numbers less than 4 of the function x squared minus 16 over x minus 4 equals 8. And then the second set of numbers that I plugged in, I get the limit as x approaches 4 by plugging numbers bigger than 4 in, is also equal to 8. It doesn't have to be the case that the left and the right hand limits are the same. But if the left and the right hand limits are the same, this is the best situation we can be in. So in this case, the left hand limit with the minus sign, plugging numbers like 3, 3.5, 3.9 came out to be 8. The right hand limit, plugging numbers like 5, 4.5, 4.1 came out to be 8. When the left hand limit and the right hand limit equal the same number, then we can remove the sign and get a two-sided limit. So the left hand limit is 8, the right hand limit is 8. Now I can delete the sign, the minus and the plus sign. When the left hand limit and the right hand limit equal the same number, then we say the limit as x approaches that number is that number. So the limit for this function, x squared minus 16 over x minus 4, is going to be equal to 8. So the left-hand limits and the right-hand limits are one-sided limit. This symbol, without the little plus sign, without the minus sign, is considered a two-sided limit. Let me maybe pause the video. This is going to be a monsterly long section because there's so much theory before we get into the problems. So we'll call this part 1 of maybe up to 4 parts. I'm not sure how many we're going to wind up getting.